Hi. No. Wow, fucking losers. All right.
Man.
Hi, my name is Pablo Galindo.
And my name is Łukasz Langa.
And this is the Core.py podcast, an established podcast where we discuss internals of CPython and our adventures in making our new version of your favorite programming language. And we should change that word. Like, it's complicated. Like, I don't know if it was you or me, but like, we put it in bold. Like, it's like the word is important. Established. It's not that hard when you say that word. Established. All right.
It's like Esteban. It should be easier for you.
Esteban.
Established.
Well, like, in theory, we say that the podcast is, bi-weekly, but like, it's all time dilation. You see, this is what you get when you record with a physicist. Like, time is a social construct. Like, it means nothing.
So we make it bi-weekly by making every episode essentially a double episode. And
exactly, yes.
The last one was already a double episode, so it's really a quadruple episode.
Quadruple episode. Wow.
Yes, maybe we should.
I think it's probably the more we extend the delay between episodes, probably the longer the episodes to compensate. Like,
no, let's not do that. No, it's a nightmare to edit later. Okay. So like let's keep to some sensible duration, like 90 minutes.
Tops. Yes, 90 minutes sensible. Well, you must know that Gukes did like some kind of like Greek heroic thing, like editing those big boys. Lots of like tricky thing, and like the levels were all the way everywhere. But that's what you get when you record outside your home with equipment you just bought in Amazon.
Yeah, it was guerrilla podcasting. Now we are back at home, and obviously it took us now like 20 minutes to actually start recording because I had trouble with my hardware. So it's not like your own hardware is like fault free. Like it's
not that you have to buy it from Amazon just 2 days before because you're a piece of shit.
Yeah,
I was a piece of shit, just in case anyone is questioning what I'm implying. I had to buy it from Amazon, as we mentioned. But names are important, and calling things is also important. So in today's episode, we are going to talk about calling things. What about that? Because like in Python, you're calling things all the time, and like a lot of people. Like, man, you see all these fucking like people on YouTube saying like, oh, a lot of people ask me, like, nobody fucking asked you, dude. Like, what are you talking about? Like, I hate when people do that. Like, a lot of people ask me, like, what is the best? No, dude, like, fuck up. Like, no, nobody asked you anything.
Yeah, there's no contact form. Like, who could possibly ask you?
Nobody asked us in Core.py. 100%. Nobody did. Nobody asked us to do an episode about calling conventions and like how things are in Python. But that's the reason we decided to do it, because like it's our podcast. It's not your podcast. You see, it's our podcast. So we do whatever.
I like this because we can start this episode with a realization I had at some point, like when I was poking at Python, that like Python is an interpreter. But that just means that it is an interpreter running on an interpreter. Because the CPU, what it's doing is essentially interpreting the next operation.
It's another interpreter. And then there is another interpreter down the line, because like, the big boy assembly, that is also a lie. There is this thing called microcode. And like,
exactly right.
Oh no.
So it's just interpreters all the way down.
Yeah, maybe that's why Python's low. Maybe that, like, who knows?
Yeah.
But we like it. But this is an interesting realization, because like many people don't even know what is the normal way this is done for languages that people like to code because they are faster. Like the illegal language. Oh, sorry, I forgot about it. The
illegal language. Yeah, or even the legal language, actually. Rust now does the same thing.
Rust is the legal language?
Yeah, but it does the same thing when you're calling functions.
Oh, Rust is the legal language. Well, it's legal.
I think because of the memory safety, that was the entire point about making C illegal.
But if Rust was like, the D&D alignment chart, what will be Rust? It's like legal.
Oh, it was really like good. A lawful good.
Lawful good, no?
Which is like, the
chaotic
good.
No? Like, it's like slightly chaotic.
I don't think so.
Chaotic, syntax is like...
chaotic good would be like Ruby, I think.
Whoa.
We would be neutral.
Python,
we would be
what is Python
neutral,
in your-
and Rust is like lawful good. You will understand the memory model. You will appease the borrow checker.
It's true. You're right. Oh, we need to talk then about the full scale. So can we agree that on the other side, like lawful evil is Java? Java is lawful evil.
Yes.
Like it sounds like fuck you. You know, like you are going to write this class.
Yes, and then C++ is like
chaotic evil. It has to be chaotic evil. It's like, you know, sometimes it's not about like doing bad for the sake of bad. Like you're not just bad because you're bad. Like Java would be. It's like you know you're bad because like whatever. Like I just care about myself, right? So I mean, it has this air of like, you know, righteousness because it's like, oh, you know, like you will put this contract and shit. But like the reality of the situation is that it's kind of like all the fucking like place, right? Like it's just like there is very few people that write really good C++. Like most C++ tends to be like this shared pointer.
Because it grew to
swamp.
be multiple languages in one, right? So like nobody ever uses all of C++.
Yes, exactly. Even, you know, something that I have seen, like even it's interesting because like when people use new versions of Python, like you start seeing constructs very quickly. Like I remember to my taste, right? Like when we had pattern matching, of course, like there is not a lot of libraries that do pattern matching, but I have seen a lot of pattern matching, more than I thought I would see. But like for instance, C++ added like a bunch of cool features recently, like ranges and async and coroutines and shit. And like I have never seen those outside my own code. So like even the mega C++ people, like they really go really slowly adopting new features. Well, I like C++. It's kind of like insane.
Lambdas
but, you
and
know,
everything, you know, it's
yes.
coming.
Well, yeah. And like, you know, it has this gotcha. Haha, you fuck up the ampersand and now your program is like 3 times slow because it's copying. Like it makes the language lawyers funny. Well, we love C++, even if it's the legal language or the semi-legal language.
You do love it. I
you don't like C++?
I have very little experience with desktop or like server-side C++. My only real C++ experience is embedded devices.
But that's a different
And it's like,
C++,
and it's a
no?
very weird world there. Yeah, like you usually just use a subset of C++ there because you can, in embedded devices, essentially statically declare a lot of memory since you know what device this is going to be working on and is not going to share that space like with anything else. So like you can cheat that way and actually it's faster somewhat and whatever. But then if you just don't like, you know, control things yourself, you can overwrite that memory from different places in your program at the same time, like very easily. It's ugly.
Right.
And yeah, and old C++, which is most of C++ code you're gonna encounter, is very different from what new C++ wants from you. So those are just
it's also,
two different languages.
it got easier, but also like it's a language where like you start talking about the rules, like, you know, the standard and whatnot. Like it's very difficult to know if like something is real or not. Like you know about L values and R values. Yes. Like you know what those are. You know that C++11 have like all this other shit like X values and GL values and PR values. You know that?
I don't know much detail about it, but yes, I was aware that.
So X values, for instance, are expiring values. For instance, like the return of a calling function whose return value is in R value, like reference, that's an X value. And like those have like slightly different semantics. And then you have like R values, which are the ones that you know, and like PR values, which is like R values that is not an X value because like the Venn diagram will have like an exclusion there. It's just wild, man. Like it's just, I mean, nothing really matters until kind of it does. Like it's just to justify why things are some way. I mean, it's easier to understand, you know, in this situation, don't do this, right? And then, you know, you don't need to understand all this terminology. But well, anyway, let's talk about the legal language for a second. This is quite fun, actually, because the legal language comes in the standard, like, you know, the C99 standard, which is what we use in CPython. Do you know, like many people don't know this, but like, you know that, well, I mean, of course, you know, like the standard is not a public document that you can actually consult. You need to pay for it.
Yes.
You need to pay for it. So
I actually tell people this because people don't understand when I tell them that Python is a public good. Because it's one of the few like technologies and languages that are not controlled by a single corporation. People are like, hey, but what about like, you know, you have C, you have C++, and there's a consortium of like multiple corporations, so they're great. And I'm like, well, download the spec and see what happens. See how easy that is.
Well, you need to pay for the
Yes,
spec, and it's not a
exactly.
cheap one.
Yeah.
Yeah. It's quite wild. I mean, there is like free versions of that, but like when people cite the standard, it's like you are citing a book that like you need to pay for it. Yeah, it's kind of like I just find it bananas. Well,
As a scientist, you should be very used to that.
of
Though.
like paying for things. Well, not really, right?
Well, like a lot of publications that like where you put your results in, like where you put your papers in, are also not free to use and are just the distribution is very limited.
Yes, but like when you're in a university, for instance, when I was doing my PhD, like the university pay for access to like most like big publications. So like as long as you're doing the request from your like university network, like those are free because like free for you. Like the university is paying for it in bulk. Of course, if you are an independent researcher, then you need to pay per publication, and it's like ridiculously expensive.
And it's
like
super
60
expensive.
quid a paper or something like that. But nobody does it. And then there is this other thing called like Sci-Hub that may or may not like have a network of VPNs that allow you to do that. But nobody will do that. Like
And you have like
totally
websites
illegal.
like Archive, like with an X and whatever.
Well, the archive is like the preprints. So like yes, like for instance, my field, which is like general relativity and mathematical physics, like normally you will put the paper there even before submitting it because like most publicators are chill with that. I know of other fields like medicine where like that's not a thing. So like, if you want to access the latest trigger finger research, then you need to. I mean, it's in PubMed, but like that is a bit more hostile. And I know that other things like biology, I think, like that's even more hostile than physics. I don't know. Physics tend to be quite chill.
Okay, we went off the rails like right away in this episode.
Yes,
we didn't even get like to the main thing.
Yeah, well, so I wanted to talk about like how normally like the abstraction that goes before Python works, right? Because like when you call a function in C or C++, then it depends on like what happens. Actually, a lot of things may happen, but normally, under like most ABIs, which is this application binary interface business, you will use something called the stack, right? Like the not a stack, but the stack. And I wanted to mention the legal language specification because the C99 specification doesn't even mention the stack or the heap by that particular reference. Did you know that? Like that is not even referenced there? Yes, like they don't care because you program against this thing called the abstract machine, and the abstract machine doesn't even care about like the stack or the heap because like that's something that is in the platform, right? What they talk about is manual memory management and automatic memory management. So the stack is automatic memory management. Like the ABI will take care of it.
Well, yes, because it cleans after itself.
Exactly, but the like it doesn't like for instance it doesn't talk about like it doesn't specify that it needs to be a continuous piece of memory.
Is
like
there a semantic difference, or are they just using confusing terminology for essentially the same thing?
No, there is a semantic difference. For example, the stack is a continuous piece of memory, right? Like it grows linearly, and then but there is nothing in the C99 standard that says that like automatic memory management for local variables, something like that, needs to be in a contiguous piece of memory. For what I care, like you could. I mean, that's how technically things like, stack switching mechanisms for coroutines will work. Like you can like heap allocation random shit and like jump to that. And like that is discontinuous.
Okay, but before we get there, like I think I would like to start at the very beginning of the story where, we are writing assembly and there's instructions that you're doing and you can jump to other things, right? So obviously what you would like to do is not to write assembly instructions like forever for everything that you want your program to do next. You will want to organize them somehow, and organize them in what we call functions, right? Which is something that accepts some arguments and maybe can also emit a result, right? Can return something. So you want to organize this, and it seems at first that all you need is really just this jump because it's awesome. You can just like put some code there and you can just jump and then just put some little like, memory address that where to come back to from this jump. So when the function ends, you can just come back to where you were before. And this is all great, but it turns out that if you want recursive functions, so you want to be able to call the same function from this function, and maybe not directly, but like by some chain of calls, This makes the super simple solution of just having like jumps and a single point in memory that says where to come back to, that's insufficient, which is why we need the stack. We need to essentially say that a single function can be executed multiple times during the same program from itself or from a chain of calls, and all of those executions will have their own local variables and whatever, and we need to store them somewhere and whatever. So the stack that we're talking about is a way for us, like in assembly, in this almost lowest level interpreter that we use, to be able to call functions, including recursive ones.
Indeed. So basically, what will happen when you call a function in assembly or C, because like C at the end will translate itself to the local assembly, like, bytecode or whatever.
Yeah.
So what will happen? Well, if you call it bytecode, but yes, like what will happen is that all the arguments to the functions get pushed to this stack, like this piece of memory, and then there is like some convention on, like, some arguments need to be in a specific register sometimes. So depending on your architecture, is this register, so this other register. So of course, like the compiler needs to know the CPU that you are going to run. So to know where to put different things, and normally you put things in registers unless there's mega, like tons of arguments, something like that. And then you need to also store the return address. The reason is because like when you finish to call that function, you need to know where you need to go back. As you may have as many return addresses as functions you will be calling, you need to store them somewhere. So you put the return address as
also
well
on
to
the stack. Yes.
Right. And one is a stack because like one goes after the other. So to access the value, for instance, from the arguments, you will need to the return address, you will need to pop everything else until you arrive to that.
Exactly right.
And then basically, as the function is running, all the local variables for the functions also live on the stack. So for instance, if I use now a local variable called x that is an integer, unless the compiler is smart enough to just use registers, because like that will be obviously faster. Like if it's a lot of like memory that needs to juggle, or like just a big chunk that doesn't fit in registers, like it will push it to the stack. And all those local variables and all that like information that the function needs to store to run is what we call a frame. It's called a frame because like you can imagine that it's all the stuff that the function needs to know what is going on. Like imagine that you are in a arbitrary point of your function, and to know like all the information that is required to know what to do next, and like the values of your local functions, and like where are you right now and things like that. All of that is what we call a frame. And some of that in C lives in the registers of the CPU, or some of that lives also on the stack. Normally we refer to all of that as a whole, depending on who you ask. Like they may not include the registers, but like we refer mostly as a whole as the frame. So when a function returns, like we have a bunch of like values. One of them is what we call the instruction pointer. So the instruction pointer tells you like what instruction to run next. Obviously, as your function goes and advances, like you need to move that forward because like, now you're executing the for loop and before it was something else, right? So you need to move the instruction pointer forward.
Right.
And then we have something else called the stack pointer. So the stack pointer tells you where in the stack you are, right? Because at the end, the stack is like a big array. You can imagine it as a Python list, of course, like very far from the real list, but like you can imagine it as an array, and then the pointer tells you like where we are. And it's a stack, right? So it can only go forwards or backwards, it cannot jump.
Exactly.
And then all of this shenanigans work because the C compiler is a very smart piece of machinery and knows the stack sizes of everything that needs to happen. So like when your function, does things and, doesn't need variables anymore or finishes and whatnot, it knows how many values from the stack it needs to pop and like how big those values are. So like all of the information is known at compile time. So basically the compiler will know how much memory is required to execute your function. That's very important because like when you enter the function, it needs to know that it's going to fit. At the end of the day, like it just figures out as it goes. But like because you will get the common Stack Overflow. Stack Overflow means that you just like ask for a lot, and we don't have that much, right? But like the compiler will know how much memory is required for your stack frames. There is a key limitation, though, as you can imagine. The key limitation is that you can have function calls, but you couldn't replicate in this model generators, because a generator essentially is a function that you will suspend and then you will continue sometimes else. But like here, you can only enter functions and exit functions. Like you cannot leave the function in the middle because the stack either grows or shrinks. Like you cannot like jump from the stack to some other place in the stack. I mean, you technically cool, but like not in the normal model, let's call. So how does this work in Python, Lucas?
Well, Python can interact with C functions. It can call to C functions, but Python's functions, when you write a Python function and call it in your program, that's something entirely different. And the reason why is that Python, as we said at the very beginning, is an interpreter on top of the CPU interpreter. So it does not use directly any of the C-level shenanigans. It implements essentially its own equivalent to everything. When you write a function and call it later, like in Python, Python creates an equivalent of the frame just for like Python's purposes. So it's essentially a structure in C that holds everything for you in terms of Python locals and in terms of Python return value and in terms of links to the previous frame. So when you're done, it cleans everything up, like it, destroys what it can, like the locals that you use and whatever, holds on to things that leaked somewhere else. So like, if you put them in any global variables or whatnot, and if you have a return value, that cannot be cleaned up. Thanks to our reference counting, it'll know that this thing actually still needs to live. But the chain of frames is not the stack in C. Like, we have our own, and it's entirely independent. In fact, all of the frames in Python are actually stored on the heap. It is just kind of data structure of a C program.
It's the most popular data structure in interviews.
Yeah.
Which is?
Like the ring buffer.
No. No. It's like linked list. It's
Yes.
a linked list.
Yes. Right. But I should really just preface my explanation with one thing. What we are now describing is sort of classic Python, which is like Python around 3.9, 3.10. Because now there is a ton of optimizations to make things faster. We'll get to those. But for now, we're explaining this sort of like bird's eye view on, if, for example, you bought Anthony Shaw's book on CPython internals, that's Python 3.9. So all he explains inside is true as of Python 3.9. In Python 3,
Yes.
In Python 3.15, the reality became much more complex because of jitting, because of specialization, because of other optimizations that like say, how about we don't create all of those Python level PyObjects that represent our Python frames unless somebody needs them from Python. We do a lot of things just to make Python execute faster, which we did not do in Python 3.9 and older. 3.10 already had like a tiny beginning of all those changes. In 3.11, they kicked in full swing with the specialized interpreter that got better in 3.12. And now with free threading and with the JIT, like the implementation internally is off the rails. It's pretty complex to explain. So we are starting at 3.9 so that you have a bird's eye view before we get to the nitty-gritty details on what got optimized how. So, high level, a frame holds everything needed to execute a function. So you have it organized in 3 main sections in memory, I guess. So the first section would be the bookkeeping data, which includes the globals dictionary. So the function can look up things that are not inside the function, right? If you import like pathlib and you actually refer to it inside your function, like how does the function know what that is? Like this is where this is stored. So module level variables, the built-ins, the code object, which contains the compiled bytecode for this specific function, a pointer to the previous frame. When we are done and we clean up, we need to execute, continue execution from what called the current function, and a pointer to the function object itself. So that's the first section. Then the second section is our locals. So the variables that you actually declare internally in the function. So that also, like in C, but again, it's our own implementation of this, stores the function arguments. and any variables that you defined internally. This is implemented as a simple array. It's indexed by position, which is much faster than using a dictionary. And like this is fun because you can literally see this if you disassemble, your function code. You will see how this is referred to. What else? Oh, it also includes the cell variables used for closures.
Cell variables.
Yeah, so if you have an inner function and it uses a variable from an outer function, we need to capture it, right? Like what that means is...
Do you know why they are called cells?
Because they capture, because they're prisons.
Because... like the stages operation.
Yeah, I don't know.
No, it's because like normally it's box values. Like you basically have an indirection there, right? Because you have an object that basically points to the object outside. Because sometimes if you declare it's a non-local, you can mutate it directly, but otherwise you need to protect the mutation because you can shadow it and things like that.
I see. So the cells are for closures, but also like any other free variables that were captured from outer scopes, like when you're calling the function. And this also is a fast array approach for those as well. So accessing local variables in Python is quicker than accessing globals.
Well, that used to be. Now it's more or less the same thanks to the Mark Shannon special, but yeah.
Right. But like the classical optimization of Python code that you might still encounter in some programs would be to bring in things into locals when you're, for example, looping over them.
Correct.
Not to like have tight loops over globals. Just like create a variable like, I don't know, J equals something.
Yeah, like you are calling math. The classic one is like, I don't know, you're calling math a square root. Like you will capture math square root into something instead of referring to math square root all the time. Mm-hmm. Because like if you access a global, you need to go through the global dictionary, and that's a hash. You need to hash the name of the function. It's just so ridiculous if you think about it. I mean, there has been even like psi optimization attempts, but like basically modulo some like very smart attempts at like avoiding this. You will need to basically hash every single time by the name of the function, some dictionary, and then just get the thing and call it. While if it's in a local, the compiler knows in what index of an array is the pointer, so you can just get the pointer with no stupid hashing and things like that.
Yeah. Right, so we have those 3 sections. I talked about 2 so far. The first was the bookkeeping data, the second was the locals, and the third one is the evaluation stack, which is a temporary workspace for computing expressions. So Python uses a stack machine where intermediate results get pushed and popped during expression evaluation. Again, you can see this if we disassemble and actually look at the bytecode. It's all stack-based. So the physical memory layout puts the specials first, then locals, and then the evaluation stack, because likely this will actually be useful the most, right? So this layout was chosen so that we know sizes of specials, right? Because like those are all essentially always the same. So Python can calculate where the locals start with simple pointer arithmetic, just like adding an address and we're getting to locals. And the interpreter maintains a frame pointer and a stack pointer to navigate efficiently through those sections.
So just before we go there, the classic other contender for the stack machine? Like you can have interpreters that are stack machines, but the other classic one is
it's a register based.
It's a register machine.
Yes.
So why do you know why Python will choose like a stack machine?
I think it was simply that like whatever literature Guido was reading at the time was implementing that, and I think that's what he went with. Was this one of those decisions that he actually weighed the pros and cons of both?
I think we can ask him as we do. So let's ask him actually, and let's come back from
as far as I know. Let's confirm. But as far as I know, this was just one of those things where.
My guess is that it's just easier, because the challenge with the register nonsense is that now your compiler needs to do register allocation, and that's a very complicated problem. By the way, register allocation is a very similar problem as meeting room organization. Like you have like some people that want meeting rooms, and then you want to like ensure that you allow different meeting rooms to be freed and unfreed at like precise times when you have a compact version of that is finite. It's just like, so normally stack machines are more compact, like instructions basically don't need to specify operands, and that makes like the instructions very dense, and that's good. It's also kind of like easier to decode because you don't have like weird registers in the middle, and you don't need to take care about that. Obviously, like the disadvantage of this is like you have more traffic. Like if you look at the number of operations that you will need to do to add two numbers, even in an interpret language, of course. Like, you will need to put, you add two numbers in a stack machine, you need to, we are going to cover this in a second, but you will need to basically push the two numbers to the stack, then like pop them, and then like, push the result back, right? And then it's like much harder to optimize because you need those temporaries in the middle.
Yeah.
So the next instructions go there. The registers normally are faster, and like you can reason about the intermediate state in the compiler, which is like, I mean, you could in both, but like it's easier to do in the compiler. The problem is that like now all the instructions are much harder because you need to include normally the register where it goes, right? Like you will say, oh, I'm going to add these three registers, and like now now you need to specify what registers it goes, and then like the problem is that you're pushing all the complexity to the compiler, because like one of the more challenging problems in compiler design is precisely like where you put in registers and where you put in the stack.
Yeah, but okay. So one thing that I never really had to research, so I don't know the detail there, is that with a stack-based machine, you can imagine that because the stack really lives on the the computer's heap, there is a shit ton of memory. There's so much memory that like you can imagine that like unless your interpreter has other limitations, you could like make the stack ridiculously deep and ridiculously like rich in like what you store in it. There could be a ton of locals. That would be perfectly fine. But when it comes to registers, there's only a finite number of them physically on the CPU, right? Like you cannot just like say, okay.
No. You are mixing two levels.
Okay.
Like you will not be using the machine registers. You will using like also made up registers.
You have virtual registers.
Yeah. Oh, okay. The reality can be slightly more complex, but registers in this regard will be like local variables in the C evaluator loop. So imagine that in the C evaluator loop, I have 10 variables called A, B, C, D, E, F, G, and those are my registers. So now,
I see.
Like I will have instructions that are store this variable in register A. That means like A equals value. The problem now is that you're jumping to a different instruction now, and then the state is not on the stack, it's in your local variables, right? Mm-hmm. So for example, imagine that now you go to, your function is a generator, and then you yield. Those A, B, C, D, E, F, G, it needs to be stored now again back somewhere, because like you're going to go elsewhere. You know what I mean?
Yes.
So now you introduce this idea now of caller and callee safe registers. It's like now who like are those values like the same? Like can the callee know that I have a variable called A? Because think about it. If you are going to use the same function, the evaluator loop, and then you call a function in this model, you could technically just switch the call object and then keep going. Mm-hmm. And then if you, for instance, calculate A plus B, and that's an argument to a function foo, when you start evaluating foo, you could just say, well, this value is in register A, which is a local. So you don't need to pass it anywhere. Like you don't need to do any fucking weird thing. It's like you and then the compiler will be fast and like smart enough that say, oh, since A is one of the caller registers for the function call, if I put the value of A plus B in that register, then I don't need to do anything else when I call foo. Mm-hmm. But you see, like now the compiler needs to think about those kind of things, right?
So it's sort of like, it's more efficient, but it's implicit. So there is plenty of opportunity to do the wrong thing.
Right.
And it's going to like return subtly crazy results then.
Yeah, and like now you can do it really badly, if you can imagine, right? Because like you still need to put like something to the stack. But like just to highlight why register machines can be better. So imagine that you're adding like two numbers, right? Like so A plus B, and then you store the result in C. Like in a stack VM, like CPython does this way, modulo sum optimization. You will have a load of A. So you push add A to the stack. Then you will have a load of B, you push B to the stack. And then you will have an operation called add.
Yeah.
And add, you don't specify what. It's just always pop 2 values from the stack, and then add the result, and then store it back on the stack. And then you will store it in C with another store. So that's like 4 instructions to do the addition. And those 4 instructions have 4 stack operations. So 2 push to the stack, 2 pops from the stack, and like the 5th one with the store, unless you store directly on C. So it's like 5 stack operations plus 4 instructions just to add 2 numbers together. In a register-based machine, you will have basically 2 instructions. One of them will be an add, but now the add will take like operands. So you say add AV and put it in register, I don't know, R0 or whatever it is, right? And that is like a single instruction, and you will not use the stack by anything. It's like you read from A and B directly, like which are locals, and then you put it in some register. So literally, you just put in some local,
right?
And then you do a move of like R0 to C, which is like storing that local into a local variable. So it's 2 instructions, 0 stack operations, and like directly local mingling. And you could even have, depending on your instruction set, an even more efficient one, which will be like add C A B, which is like add A and B and store it in C, and like. If your instruction set will take also local reference, not just registers, then that will be a single instruction. So it's not only smaller, but like it's much easier to, but it's more dense because like now your add takes values and like the compiler needs to know where those values are and like where they will go. Makes sense?
Yeah, it makes sense.
And then if you compare, like for instance, if you are, I don't know, adding 2 things and multiplying them, like so I don't know, A plus B times C plus D, those will be like 9 instructions compared to just 3 in the models. So that's like, and then it has been some attempts to do this in Python, but like it's a fact sheet of complexity and it's not necessarily faster for everything. Like here in this example I'm telling you is the classic one when like the stack machine is worse, but like there are other more complex ones where like it's not clear. Well, I suppose Mark Shannon will have opinions, but
yeah.
Well, anyway, as a way, if everybody's listening to this and is like, what the fuck is happening? Like, let's trace together basically what will happen if I do A plus B times C, right? So what will happen here is that Python will execute this operation basically step by step, and it will use like this stack, this local stack to store all the intermediate results, right? So first it will load the value of B because like B is in some local variable and needs to put in the kind of a scratch path, right? So I just bring it to my local array of memory when I can start doing things. So that basically is on the stack. So you just imagine the stack as a pile of things. So you just have one now. So the stack now has B.
Yeah.
Then it will load C because it needs to do the multiplication first. Because remember that we are doing A plus B times C, and B plus C goes first.
B times C goes first.
Yeah. So it then loads C and it pushes on the stack. So the stack now we have B and C. So one C above B. And then it executes the multiply. So basically it takes both B and C from the stack. So like it just like takes them out of the stack. So the stack now is empty. It does the act on multiplication, which is some complicated thing, but like let's assume that it just happens. And then the result is like whatever, let's call it B times C or BC or whatever it is. And then that will be pushed to the stack. So now the stack has the product on B plus C. Now we need to continue to add A, so we need to also load A to the stack. So now we have BC and then A. BC is the result of the multiplication.
Yeah.
And then we need to execute add. So we pop both values, like the multiplication result and A, and then we add them together, and then we just push it to the stack again. So the stack has basically the result of the whole operation. And finally, because we are storing that somewhere, we need in Python will be a store fast. That means that we are going to put the thing on a local variable, which is not the stack. The stack is just like a scratch pad. It's like a whiteboard that you will have to do the operations. But then finally, you will need to put this somewhere that the user can use in the program. Like that will be a store fast to a local variable called, I don't know, like result or calculation. So depending on how you execute it, normally like the stack will basically be an array of memory, but normally you will say that the stack grows upward in memory. That means that pushing means that you increment a pointer to the next slot. Like you can imagine as a list. So you call list append or list pop. Basically, that's the idea. And of course, like, even if technically you can have as much heap as possible, Python has a limit for the number of stack frames that it can create based on not on the memory itself, because like a Stack Overflow in C is based on size. So for instance, bigger functions will consume more stack than smaller functions, and you will have a maximum size. Let's say like, I don't know, a megabyte or whatever it is. And then that means that when you reach collectively a megabyte, it will do a Stack Overflow. But in Python, it's based on number of calls. So technically, calling some functions is cheaper than calling different other functions. But we have a limit, or at least we used to have a limit based on the number of calls. That means that calling, 1,000, I think it was 1,000, no? Like 1,024.
It was 1,000.
So 1,000 functions that are super small will cost you as much in this term that like calling 1,000 functions that are ginormous. So it's slightly different way to look at that.
Yeah.
Right. And then like that's a single frame. So that would be a function that is calling a plus b plus c. So now the question is like, when you call more and more functions, you basically need to know who is calling you. Because like when you finish your operations, you need to go back to your caller the same way. So in C, that will happen because like the assembly itself will when the function returns, there is instructions that the compiler has placed for you to jump back to like, clean all the variables in the stack, like pop them from the stack, and then, jump back to change the instruction pointer to some other place when you need to execute, and then the stack will be basically as it was when you call the other place, because it's like you just keep adding things, and then when you finish you pop things. So when you pop all the things that you use, then you are back on your caller. So in Python, the problem is that we don't have like a stack pointer per se, like a text segment and all those things that C uses. So the way we use is this linked list. So all the frames are in this linked list. So the idea is that when you finish with a function, you look in the frame. It will not only tell you which is the previous frame, so you need to go back to that frame because you need to recover the local state of things, but also you need to know like in what particular bytecode offset, because like of course the you cannot restart the function that called you that from the beginning. You need to continue where you were called. So you need to also look at that thing. So when a function return, you basically reverse the sequence, right? The current frame is destroyed and freed, as opposed to allocated when you call it. Then the previous frame becomes the current frame again, and then like that's the call stack. So when you have A, B, and C, you will have 3 frames for A, B, and C, and then when you finish C, you basically go back, and then that is per thread, because every thread will have one version of this, right? So the thread state structure that we have in Python, every thread has one of these structures, keeps track of which frame is currently being executed on that thread. Because like if we have 3 threads, we'll have 3 frames executing. Of course, the guild will prevent those things to happen at the same time, but technically they switch among themselves. And different threads, then they have completely independent call stacks, and they don't interfere with each other. The important thing as well is that this is very important, because when you have an exception, you need to also unwind the stack. So you need to, you have an exception and nobody catches the exception will bubble up until someone does. So, if that happens, we need to follow those previous frame pointers to build the traceback. Like the traceback that you see when the exception blows up, that is constructed by following those pointers, those previous pointers, until either someone catches the exception or like nobody does, and then like we just use all the pointers to just print whatever it happened. And that is why it's in reverse order, because you start from the bottom, and then you just keep adding from the bottom instead of like from the top. Because if you want it from the top, of course you could reverse at the end, but if you started from the top, you don't know what is the top thing. You just know what is at the bottom, and then you need to go backwards. So it's basically walking the linked list. Everybody's favorite operation. Yes. And that means that, the last piece of the information is that when you execute a function, you need to know where you are in the function. And that means that because the function is going to be compiled into bytecode, then you will have some equivalent to the instruction pointer. In Python, it used to be called slightly different, but now it's called the instruction pointer. And that basically, instead of like being a pointer to the text segment of some executable, in Python is basically an offset into the bytecode. So what instruction are we, right? So you will have load fast, add. So it's like 1, 2, or 3 in this case, right? So when the compiler compiles this, like, Python compiles all the source code into bytecode, and that bytecode is stored in the PYC files that eventually end in the code objects. And then basically the frame itself will have an index in the code object. This is very important because this means that you have a function and then like a recursive function or something like that, like Fibonacci, right? So it will only be one code object for Fibonacci, and that's the same every time.
Exactly.
Every time you call Fibonacci in a different recursion, the frame itself will know at what offset it is in the same code object. So you will have, let's say you call Fibonacci of 10 and then you have 10 frames or whatever it is at some point, or factorial of 10, you will have 10 frames. And then every frame will have a different offset into the same array of instructions, because we don't need like one copy of the array per frame. We just use the same code object and the same bytecode. But of course, every function call, every time you call a function, it needs to have a different offset.
Yes.
So this is what confuses a lot of people, because there are 3 concepts here that interplay, right? There is the bytecode, the call object. Then there is the frame, and then there is the function.
Yes.
Right? So the ownership model is that the function owns the call object, and that is one of them. Like there is one function.
One-to-one.
Yes, because the call object doesn't have, like you can have a call object, like you could think about that. You could have a call object that is set in two functions. It's just that one is called foo and the other is bar, but it has the same instructions. So you don't need to have like two call objects that are going to be the same or something like that, right?
Right.
And then, the function will have more information about, like, even if it's only one of them in the entire program, it will have more information about things like, for instance, you have like constants in your function because you're using the number 6. We need to put that constant somewhere. It cannot be technically, well, I mean, depending on how you do the model, you could put it in different places, but like the function will have more, but there is still only one of them. And then when you call the function, then you create one frame. Every time you call the function, you have a different frame. And then the frame will know, the offset in the call object you are and the actual value of your running code. Like if you are doing operations, then you store the different results in different local variables, and those results will be on the frame, not on the function. The function is just all the constant state. That's the main difference.
Right. You already mentioned exception handling. So let's, again, like I'm going to be the guy like who takes a step back and actually thinks about like what happens inside the interpreter when an exception gets raised. Since normally what you do is you have this instruction pointer, right? And you execute bytecode instructions one by one, some of which might be calling functions. So then you create this new frame and, like create the new locals. And again, you have a new instruction pointer, maybe on the same code object, maybe not, but and you go and you execute. Sometimes like it's going to be funny because it's going to be a loop. So the instruction pointer is going to go up and down, because there's going to be essentially an if test to be made whether the iteration is still going. But even the loops, actually, depending on what you do, might raise exceptions, right? And then the exception is going to be finishing the loop's execution. So how does that work? What is going on? Well, so if any code that you are calling, whether it's Python or C, raises an exception in Python, the interpreter needs to know, okay, where should I call the next thing? What should I call next? There's an exception that appeared. So what should I do? So when your user code has a try except, there's some block, and with the except block, like you're gonna declare that like I want to catch OS errors or stop iterations or key errors or whatever else. So the interpreter needs to now find that try except that matches. It will start in your current block, in your current function that you're executing right now. It will try to find at the current frame, like, is there something that handles this particular thing? If it finds it, it will jump to that handler's code. But if not, it needs to say, okay, this line that we were executing right now, this bytecode in particular that we were executing right now failed and an exception was raised. Let's go above to the stack frame above and see if there is an exception handler that covers the current instruction for the call. Now we are no longer looking at the bytecode that raised the exception. Now we're looking at a handler for the function call that we were in, right? And then if that is not working, we're going to the stack frame above and look for the exception handler that covers the function call to that previous function call, and so on and so on. So you will essentially like go up the stack looking for exception handlers. And if you fail to find any, well, then Python has this built-in way of dealing with exceptions, which is simply just to show you the traceback and say, okay, this was unhandled, something crashed. But if there was anything there, it'll execute that, and maybe that will handle the exception without re-raising, without it spilling all of the execution all the way to the module level of the entry point to your application.
This tells us also some interesting information that maybe people want to retain, which is like that is why raising exceptions is slower. Not only that, it's slower the more try excepts you have in your function, because like when Python needs to know if there is like an exception block that matches the instruction pointer. They need to. I mean, you could do binary search for sure in the instruction offset and whatnot, but you need to basically, the stupid implementation will be a linear search over all the handlers that are in your function. So of course, like, maybe you have 10 try except stops in the function, but you have a stack frame that is like 1000 deep. You need to do this lookup on every function and then, adjust for some function above you to catch it.
Exactly.
Yeah. Especially you have control flow that is based on exceptions, like Python does sometimes with stop iteration and whatnot. Like you will need to basically do linear search over all the handlers, and then follow the pointer and then keep going and follow the pointer and keep going. So it's true that most of the time you probably want to catch it very close to where it happens, but if you don't, like you probably will be paying for exceptions quite a lot. And even if unwinding is kind of cheap.
Well, if they happen in a tight loop, then yes. Yes, the rule essentially is that creating new try except blocks is not costly at runtime. It is a tiny bit costly for the compiler, because we need to create essentially a table of all those exception handlers such that every code object has a table like this, so that the lookup is faster, right? So we don't actually have to like go over every bytecode and seeing like, oh, which exception handler is that in? Is there a try except around those guys, like, and so on? No, there's a table that you can query essentially for knowing whether bytecode raising an exception will be handled right away in our code object, or do we need to go to the stack frame above? But raising is expensive because of what all of what Pablo said.
This is also the new model, because the old model before 3.11, what used to happen is that what you do is that when you enter a try, there is a small cost of entering the try, because it was the instruction used to be called, I think, setup except or something like that. Mm-hmm. So what will happen is that you will push the handler into some specific, like the handler here is a structure, right? So you will put this on a link of like handlers that are active. It needs to be a stack because you can have nested exception blocks, right? But you will do it, they push it. So when you raise an exception, instead of like trying to see if there is a handler for your instruction pointer, you will look at all the handlers that are active, right? So let's say you enter a try. So you push the handler, and then if there is an exception inside the try, you will say, oh, is there a handler for this? And then that answer is immediate because you have the structure somewhere, right? So you say, oh, the list of handlers is not empty. So now you need to check if the handler will manage your exception or not. And then if you have two nested try excepts, then you need to check the outer one as well. But you will know which ones are applying. The problem of that model was that even if no exception will happen, which you will say that that's the normal case, you pay all these like pushes and pops from the handler code. Yeah. So this means that exceptions are like try excepts were not cheap. Mm-hmm. They were cheap but not zero cost, which is the term.
Cost. Yeah.
And because the reason is that you need to pop and push every time you enter and exit the try except. So imagine, for instance, you have a for loop, and inside the for loop you have a try except. Mm-hmm. Like that will mean that you are doing all these pops and pushes from the handler state for no reason. Because for no reason, like if nothing happened, right? Which means that your thing will be so much slower. Like it will be so much better to basically wrap the entire for loop in the try except, not the other way around. While in this model, then the programmer doesn't need to think about like where is the handler. Like that will basically be calculated. It's a kind of like a gamble a bit of like normally you will not raise exceptions because exceptions are exceptional. But of course, like if you're raising a lot of exceptions, then like the problem reverts. But it's the right model.
Yeah, and with stop iteration and some other protocols, it's the expected way of things actually proceeding. So Python is pretty exception heavy, and also as like the Pythonic things that we are expected to do very often are operations that potentially cause exceptions, because like that is better to raise an exception than to return a status code, right?
And when you exhaust an iterator, it raises a stop iteration, right? Yeah, so like there are exceptions that are normally used for control flow. Big mistake, by the way, but you could return a sentinel value or something like that, right? But choices were made. But yeah, The interesting thing, so we are going to talk about optimizations because there are so many here because it's such an important part of CPython. So we are going to talk about optimizations in a different episode. So we are doing now these multi-part episodes again. But I wanted to, because we mentioned it a bit, we keep referring to 3.11 as the big thysma of like frame evaluator or whatnot. So one of the big changes that we did in 3.11 is that before basically 3.11, every single function call basically allocated memory. It allocated a Python object, an entire Python object with reference count and all, called pyframe object. And that was a heap allocated object. So this means that every time you call functions, we call pymalloc, well, not technically pymalloc, but malloc, and there was a lot of optimizations on top of this, like linked list and free list and whatnot. So really, that malloc didn't really allocate like most of the time, but they could. And not only that, like there's a lot of overhead because they are Python objects, so you need to manage the reference count and whatnot. And so a lot of operations needed to be done just because it's Python objects, and those were basically like 300 byte structures, like that you need to allocate. So in real Python code with a lot of function calls, basically you are constantly allocating and freeing these frame objects. And actually the kind of expensive call is actually free, because when you free the frame object, you will either need to put it back to the free list. So there's some operations for bookkeeping, or you need to call free, which needs to basically, put the memory in some slab of memory and like manage the entire thing so someone else could use it. And that happens every time you return. So returning actually was the expensive part, not calling. And then the problem is that all those malloc and free calls basically add up, and then also memory will become fragmented. This is the other problem, because if you think about it, calling functions, like, when you call a function and you return, you know where you're returning to. So if all these frames were in different parts of the heap, this means that every time you kind of like undo the call, you will need to use a totally different memory and access a totally different memory part. So it's very difficult that will be in the CPU caches. Like, of course, like we are not using registers and whatnot, but we are accessing memory. And if that memory is already on the cache, then, calling, like returning will be or even calling, it will be very cheap. But because every frame is in a different place of the world, like every time you return, now you need to throw away all your caches and then load them again with all the information. So that's bad. So the idea is that we have is that most function calls never need their frame inspected by debugger or introspection tools. So this technically we don't need even Python objects at all, right? Like sometimes you need, right? Because like there is a bunch of things that look at frames for different nefarious reasons. But
it's just like loggers, right? Like that want to know.
Yeah, for instance, loggers do. Yes, like if you need the call stack, you will need that.
Yes.
So loggers will do. Sometimes, but like not all the time. But like the baggers will do. PyTest does all the fucking time for no reason. Some certain frameworks also do for also no reason, but like we are not going to name them. But yes. So yeah, bad thing. So the idea is like, ideally we don't even need the Python object at all. We can have like some nice CS structs. So the new approach that we did in 3.11 basically splits a bit the concept. So we'll have basically a super lightweight internal CS structure called PyInterpreter frame, because we like to make everything extremely confusing. So now we have PyFrame object and PyInterpreter frame, like with an underscore, just to which think about this, because remember this detail, because it's going to be very important when we talk about things that we broke by doing this. And this basically has exactly what is needed for the execution and nothing else. So all the data that the buggers will need and whatnot, that will be calculated lazily. And the idea is that we will have that. And then the full Python object basically only gets created when someone really wants it. So we don't really create like the rough counted version of this thing with all the debugger information. Just like, we have and we have to maintain also that structure, because if someone looks at the frame, well, we cannot just change the fields and whatnot, which is like ridiculous, because like you cannot do optimizations now. But like now in this PyInterpreter frame, which is private, we do whatever we want. And basically the lightweight internal frames basically are allocated in a per thread stack using what is called a bump allocator. So the idea here is that we like BRK and SBRK, the function calls, but we just use something like that. So instead of like basically going and saying, oh, I need one of these new ones because I'm calling a function, like instead of like going and calling malloc and blah, 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 basically what we do is that we call like a huge malloc at the beginning of the program, and then that is like a slab. And then every time you call a function, we just use that chunk of memory, and every time you return, we just like, move the pointer back. So basically we have our own stack. We just created our own stack by hand.
But it's more similar to the C1 now, because we are now limited by size and
exactly
not by number of calls.
except that it could be, because every function call needs more or less of this, it could be that you are still under the recursion limit that Python has, so under 1000, but still, it could be that you just call a mega function and then we run out of that. So we cannot stop there. So what we do in that case is that we allocate another mega chunk of memory and then we link them with a pointer. So technically, what Python has is a linked list of stacks. So instead of the stack in C, which is contiguous, is all contiguous memory that is reserved and blah, 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 depending on the ABI, Python for frames has a linked list of stacks. So it's the same idea in C that you go back and forward, but like if you call, like you need more, then basically you need to do these mini jumps, like between the slabs, if that makes sense.
Yeah, and this linked list of stacks is on the heap. It's not on the C stack.
It's on the heap, indeed. Yes, it's a heap allocated linked list of stacks.
It would be
Correct.
somewhat mind-blowing if it was on the C stack, because then you would have like a linked list of stacks on the stack.
Yeah, that is how is this called? Host coupling.
Yeah.
When you use the hosting language structures to just use your thing, like that's bad because like that means that you couldn't implement generators.
Right.
Among other things. Well, technically, this also means that you cannot implement generators with these things. So if
We're
you
gonna
use
talk
generators,
about generators and coroutines and all of that
Yes.
async stuff next time, since that's pretty fascinating, but like we'll require a bit of time to explaining and your attention. So yeah, like
Right.
the actual intro to async IO and why coroutines are as they are in Python, that comes next time.
the gist of this optimization is that, instead of allocating these 300 byte structures in the heap for every call, we just bump a pointer and basically 10, 20 bytes or whatever, depending on the locals, in this like slab thing. And unless you use generators and coroutines, then normal function calls are so much faster because like that memory is contiguous most of the time, except the jumps, but it's amortized contiguous or something like that. Right? Let's call it that way.
Yes.
It's contiguous and it's also very small because you don't need to allocate the entire thing. Like you don't need to allocate all the debugging fields and all the bullshit. You just need to allocate the local references and like the minimum that is required to run, which again is like 20 bytes, not 200. And then moving is linear. So like it's normally on the cache and everybody's happy. And because this is per thread, like all those caches will be per thread, which normally hopefully will be in different CPU cores. So like this is super, super, super cache friendly. And indeed it's so. Like this was one of the biggest single optimizations that we did in 3.11. And it was so much measurably faster compared with the previous version, even if the model is still the same. We don't fundamentally change things.
The kind of crazy thing about this optimization is that you want to optimize Python to make it work faster without sacrificing existing functionality. And the existing functionality of sys._getFrame is, as we already covered, used pretty extensively by PyTest, loggers, frameworks, and all other sorts of guys, like both from Python code and from C extensions as just C APIs. So every now and again, Python needs to know that, somebody asks me about a frame object, and in that special case, actually create that expensive full PyFrame object. So that is still being done, but lazily, only in the case where we know that there was a call that will want that object. And this complicates things pretty much because that makes it such that this frame is now a PyObject. So it also undergoes the rules of Python memory management. So we cannot let it go so easily because if you hold a reference to it, well, we need to store that. And with that, we need to store everything that frame touches and created and whatever. So it's a pretty hefty operation. And if you did not see big performance wins with Python 3.11 and 12, that might be partially why. Like you might actually be using a framework or yourself, like some piece of code that relies on recreating those expensive PyFrame objects.
Right.
Yeah, we internally call this like lazy materialization. So like normally those frames are not materialized, but they can if the user code requests some PyFrame object. And like the measurement that Mark Shannon did at the time of creating this optimization was that like below 2% of function calls actually trigger frame object creation. So like 98% and more just use the lightweight internal frame. So that means like in normal circumstances, you should be saving a lot of computation. And because of this memory contiguity, even just the regular access to the same information is faster because the CPU will already overfetch and it's all like cache local. It's amazing, right? So all of those CPU caches that we have like are going to be much more effective with this approach. And yeah, like I think this is where we need to stop at this point, since we were babbling for close to an hour right now about this. Next time, as I said, we're going to be talking about the generators and coroutines world and more optimizations that make all of this work better, but make it a little harder to just naively look at the source code that we have and use outdated debugging and introspection tools, because now we have new ones that can traverse all of this newfangled world, but classic ones that expected essentially Python frame to be exactly the same as a C frame, well, that is no longer really the case. So we'll cover all of that next time.
Indeed.
But now...
PR of the week.
I have one. So I have PR 141646. So I'm very proud of this. I've been working on this for the past 2 weeks, I think. And so this is in the new
Mega profiler, yes.
The new Tachyon profiler that you know, because we dedicated an entire episode to this. Many new cool things happen. Well, are you confused about that or what?
No, I'm just very impressed about like what you're going to talk about. So, tell us.
Yes. So I was chatting with my friend Laszlo, used to be my manager. But so Laszlo was basically saying, you know what, we should do one of these like top things. So instead of like having a flame graph or whatever for the profiler, it would be very cool if we have a terminal UI or some sort, like a TUI, that basically like shows you like a top-like interface with like all the functions like appearing and disappearing and whatnot, like as your program runs, so you can know like what your program is doing in real time. That would be very cool. The problem is that if you will be doing this outside the standard library, you will use some of those like super cool libraries that the cool kids are using, like Textual or Textual, because like Rich is like not really a good choice here. So Textual, right? The problem is that we live in the standard library, so we only have sticks and stones. And that meant that, you need to implement this thing in curses. Curses, yes. So I said like, no man, like that's horrible. So I didn't do that at the time. And then, I was thinking about it and I thought, oh man, it will be so cool. Like it will be amazing. Like this is the thing. So I spent like a fucking caveman 2 weeks. like using sticks and stones, like coding this like insanity 2i in raw courses. Of course, like not the C version, but the Python version, but that doesn't make it better. And like, it's fucking amazing. I'm so happy. Like, so this landed recently. So thank you, Savannah and Laszlo, for the reviews. But this is amazing. Like, so you use this by passing this live to the profiler, and then it will show you this like 2i, and like as you're going, like it will show you like what functions are taking more time, and you can sort them by different fields, like number of samples, or like for instance like cumulative samples. So you can check like the top level functions or the single level functions. But then I just went bananas, man. I just started adding all the different like introspection capabilities that I added to the profiler since we last talked. So now, I mean, this is also available on other formats, but one of the things that the 2i will also tell you is that, it has this view of threads, like different threads will get, like you can switch between threads, and something that will tell you is like for every thread, it will tell you what is the percentage of the time that thread has been using the GIL, or how much is the percentage of the time that thread has been just waiting for the GIL to happen. So basically waiting for another thread to give the GIL back. And what is the percentage of the time that the thread is running the GC? So you can know like, oh, this thread is really just like spending a lot of time doing GC for whatever reason. And then you can also know what is the percentage of time this thread is running like outside without the GIL, like running native code or whatever it is, or like, if you are using wall mode or whatever it is, like so you can see sleep calls. If you're using CPU mode, then the sleep calls will not be there, but like, it will be something else like NumPy or whatever you're calling. So and then it has like all sorts of other things, like it will show you in real time, what is the efficiency of the profiler, how many samples are failing because like the program is moving too fast or whatever it is. You can change the refresh rate, so if you find it that it's updating too fast, it will show you like, you can change that. It will show you like the trader thing, like when when a price goes up, it will show you in green, and when a price goes down, it will show you in red. So like it will allow you to see what functions are changing. So like you will see immediately what functions are moving faster and what functions are just not being called anymore. So with this like red, blue, which is horrible. I know I'm colorblind and I don't see this correctly, but I know that people like it. So maybe we need to hook this into the colorize module so people can change the colors.
This is for 3.15, just to like be clear. So there's still time. Yeah. But like, since I'm already talking, let me just like say one thing. Like, Pablo is telling you exactly what this is doing, but like what he is super underselling is like how this actually looks in practice, because it is essentially like an equivalent of like htop, but what it is not like showing you is processes on your computer. It is showing you like how many samples are you getting, the top samples that you're getting like from the process that you are profiling, and you can order, like you can change ordering in this table by column. Like, so you can decide whether you want to do by number of samples or by total time or by cumulative time, or just alphabetically by function name because you're interested in a single function. Like all of this is colored. There are emojis literally, like it's all of this is like it's
which in courses was not trivial. You need to activate this like stupid Unicode like mode and shit.
Yes, I know this. Like you also don't know, but you will know now because I will tell you that there are unit tests for all of this crazy stuff. So like, man, like this is a pretty amazing addition. I love to see it, and it's one of those things where if you see it, you're like, cool. And you start using it and it's great, but then if you move to a Python version that doesn't have it, then you immediately feel like you are in the past, that you are in a previous generation. That like it's just like, no, this is bad. We should have it always.
One of the things I'm so happy about this profiler is that it can profile itself like it's nothing. So like every time I'm implementing any of these things, I use the profiler on itself. And what is better, I use the profiler on itself on the live mode as well, so you can see the live mode of the live mode. The innermost terminal will superimpose the other one. So it's so cool, man. Like I thought it was going to be a gimmick, but like it's so useful. Like and it's so nice because you can see if your program starts doing different shit. Because like at the beginning, for instance, the profiler at the beginning will calculate it will accumulate the samples, and then at the end it will just create the flying graph or whatever it is. So you want to distinguish those two moments, and the flying graph normally will not. Like it will just show you the total aggregation. So if one of those things takes more time than the other, you will lose it in relative terms. But in this particular thing, like it's so useful because you can see like how the program is doing different things.
Exactly.
And man, this was a beast to also test, because like this is one of these pieces of code that unless you really structure your code really well, like it's a fucking nightmare to test. Like because all this courses nonsense is like you don't want to go through that. Like you don't want to spawn a terminal and like look at what the terminal is doing, because like it's just insane. So I use this like model view controller kind of thing, when like you have like different abstractions and like you need to structure your code like so you can unit test all the different things that don't know about courses, or like just know about the constants of courses, and then the actual driving part, like you will mock shit out and then you will test as much as possible. I think this has like half of the code for this is test. Like it's just literally half of it.
Yeah.
Or even a bit more. So because like very difficult, and it has all sorts of shit. Like I don't know, if you run it, if you resize your terminal, it will be responsive. Yes, it will show you more columns or less columns, which is like you need to code that shit. And like it will also select which columns are more important. I will try to hide that. The header will show you more fields or less fields. For instance, if it's too small that my algorithm breaks, it will show you a little rectangle that says like, this is too small, please resize. Or if you start in that mode, it will wait and it will wait for you to resize before it actually starts, so you don't lose samples. So like I put a lot of effort on the UX of this shit, so like it's really good. And people like to use it.
Yeah. Like there's even like, since it's a profiler, its own performance is really important. And this thing like is very quick. It literally has a bar there where you can see like how efficient like is like the collection like itself, so that like whether you are affecting like the process or not, and like whether the quality of data is good enough. And like it's just incredible. I love it. I think like that this is the sort of magic thing that will differentiate Python from other languages, that we want to really be introspectable. Like we need to be the language that is understandable in the deployed state. So you should be able to profile this, to debug this, even on a VM that is somewhere in the cloud. You should be able to look into those processes, because this is where most bugs get unaddressed, where it's not possible to easily recreate a real production issue.
Right.
But if you can look into it as it's happening, this makes all the difference. So
right, and it works with any other option of the profiler, which means that you can attach to a running process and see it live, and then detach.
Yeah,
so like without
exactly.
affecting the application.
Right. That's so incredible. Love to see it. And one more thing. This podcast usually does not have a sponsored segment, but it's the end of the year, and the Python Software Foundation, also known as the PSF, that employs me, that is the charitable organization with a mission to promote, protect, and advance the Python programming language, now runs a donation drive that you can find under donate.python.org. So if you want to keep Python and its community strong and sustainable, go to donate.python.org to donate or become a member, read stories from the community, and check on the fundraiser's progress. The website actually looks pretty impressive, and our goal is actually inspired by the number pi. We're pretty close to getting there, so if you can help us actually get over that finishing line, please go to donatepython.org and help us help you and stay independent from corporate influence for the years to come. Since we spent an entire month without an episode, we collected a large backlog of changes in Python. So let's talk about those in What's Going On
in CPython.
So let's start with features. Serhii Storchaka added a thing that allows defining the dunder-dict and weakref slots for any class, enhancing flexibility in class design. So this change enables developers to optimize memory usage and performance by controlling attribute storage in subclasses of variable length types. So that was described in issue 41.779. So it is an issue that is only 20 years old. It actually is from March 2005. And finally, right now, we are addressing this with Serhii's PR from just 4 days ago.
Doug Woods, which I don't think we know the real name. I suppose maybe that's the real name, so apologies for that. So they added PyDiff set default ref to the stable API. So like that is something that we were using quite a lot internally, but like, a lot of people were using it. And the idea here is that, by adding all these functions to the stable API, like people can compile all these C extensions without having to rebuild which is very important. And unfortunately, like one of the reasons that one of the things that happen when you use the stable API is that because you can only use a very small subset of functions, those normally is slower, or you are like much more restricted. So in this particular case, like the idea is that now like people using the stable API can leverage the what is basically by default in a better way. Yeah. So this issue, it was pretty recent. Actually, I think he just proposed it, or they proposed it like 5 days ago, and like it was just merged 5 days ago, very fast.
Right. Yeah. Cool. Victor Stinner promoted _ PyObject dump to a public function, which is called somewhat discouragingly PyUnstable object dump. But that is only an explicit way of saying this is not part of the stable ABI. But it is now something that you can depend on. Like the alias for the old thing is maintained for backwards compatibility, but essentially this enhances the CAPI by giving you a debugging tool for developers, which is something that already people who were doing a lot of CAPI were using all the time. Now it's official, you can use it to see what's inside your PyObject, since on the Python level, you can essentially use the interactive shell or just the venerable print or anything else, like to just print out whatever it is inside your PyObject. On the C level, everything is PyObject star, and you don't really know and how to actually print them. Not so easy. So this PyObject dump function.
Man, I use that all the time.
Yes, exactly. Same here.
All the time. Like
so like I am a little bit like
yeah, that the name is longer.
The name is way longer right now. Like that's something I don't particularly love. But if it's only for debugging, you can continue using this alias kept for backward compatibility because, whatever, it's just for debugging. It's as if you had there was this tool at some point, right? Like for Python, just called Q, the letter Q, that somebody just put this on PyPI. That was essentially like a similar Python level version of this idea of make me like a debugging friendly output of whatever object. So PyObject dump is the C level thing.
So then a small one, but we want to highlight all contributors that are adding new things. So Krishna Chaitanya. So basically this is a small one because the IP address IPv4 and 6 network host call. So basically to get the list of hosts for a given IPv4 or 6 network. Basically it was kind of inconsistent on the return value. Sometimes it was returning a list or sometimes an iterator. Sorry. So now it just ensures that it returns what it says it should return. So small one, but also important.
Yeah, currently a lot of those features are very targeted small ones, but important ones to the people who are depending on those things. Like this one by Sharktide, which enhanced tkinter's text search by adding options that were in Tcl but were not exposed by tkinter. Those are no line stop, all overlap, strict limits. And that essentially expands what you can do with tkinter, with more flexibility in how you can implement search features in your graphical user interface application.
Yes. One that I'm particularly happy about is that, so this is from the sprint, if you recall. So Bram Booker finished finally his PR to Tachyon, adding basically the ability of Tachyon to see GC frames. So the idea is that now, this is what the 2i is using actually. So now we can know if a particular thread is running the GC, and then we will add an artificial GC frame showing you that something is happening under the GC. So for example, let's say you are running some finalizers or some del methods or whatever it is, and that is taking a lot of time, or it's the lock or whatever. Then you will see an artificial GC frame, and then underneath you will see the finalizer, so you know that thing is running under the GC. And then we also use the fact that there is a GC frame in the stack as a way to efficiently see if a given thread is particularly running the GC in a sample. He added also the possibility to see if the Python machine, the Python VM is running native code by also adding these native frames. The disadvantage of this, of course, is that we don't know what it is because it's native, but like at least we tell you that so you understand. You see a frame, and under that there is like half of the frame has this native artificial frame. You know that half of the time the frame was running something native, and some of the time it was like just running some Python code. So very cool, and this actually unblock a lot of other features. So very nice.
Cool. I haven't talked about Sierhi Storchaka for a long time, so let me mention another thing he added, which is nice because it is touching on a piece of code like dear to my heart. So you might have heard about functional single dispatch. That is this sort of type-based dispatch on the first argument to a function. And because of how methods work in Python, how they are bound to the instance of an object, and so on, we need to have a separate decorator called single dispatch method that allows you to do a similar thing on instances, just so that the self that you don't want to dispatch on, obviously, is skipped, and then all the arguments that you are using, like the first of them, this is the one that you're going to be dispatching on. So functool single dispatch method had a limitation, arguably a bug, where it only worked on a descriptor-based callables, which regular methods are. That's great. But if you tried to put, to register a single dispatch method that was a class instance, because they can also be callable, right? You can have a class instance that has dunder call, or you could have a lambda, literally like in your, testing code or whatever, and just pass it to single dispatch method. That would crash because it tried to call the dunder get method on that handler during dispatch. So this is now fixed here. He made it such that it is much more flexible, and developers can use a wider range of callable types in their single dispatch methods. So thanks, Sierhi, for that.
All right, and then we have one that was open, one issue that has been basically open since I think 2017 for Mark Barn. Well, the person fixing it is Mark Barn. We when we introduce Pathleaf, we have this kind of like unspoken rule, or maybe it's spoken, but like that many of the things that will take a path as a string should take also a Pathleaf object. But apparently, like the wave open, this kind of function from the audio module and whatnot, like it was, it didn't support path-like objects and bytes. So now, we added it. So fixing this issue from 2017. Yeah, very cool.
Yeah. So I haven't mentioned Sierhi Storchaka for a long time, so let me mention yet another thing that he did. So we have syntax warnings during AST parsing, and they use this functionality that like sets up the warning context automatically. It's like pycompile warn, and the file name is always correct there, but the module name was inferred, and sometimes just not like actually what the real module name was. And this was especially an issue when trying to ignore specific errors in a CI environment, like with PyTest, or where the module was suddenly something that was importlib._bootstrap or something else. So Sierhi made a change where now there is a module parameter to the compile built-in function and related functions. And this allows this filtering to work. So if you have syntax warnings or other stuff that relies on precise module names, now you can have this, and there's not going to be any of that frozen built-ins, like stuff that obscures the high-level module name that you would want to filter on. So another improvement by Sierhi, thank you. And let's move on to another section of this what's going on, which is free threading. And Sam Gross.
All right.
Big fan of the guy. He fixed a race condition in PyImport add module ref. It was a fun one to ensure thread safety during module imports. So if you have multiple threads, very often what you sort of expect that they're going to happen is like your application is going to set up, is going to start up and whatnot, and then you're going to be spawning threads. But it is entirely possible that you can still be having like an application that is so parallel that it imports things when it needs to import things. Yeah, I'm hearing this might actually happen more often, like in 3.15, huh?
Very important.
Than before. So, given that imports are now being like pushed to be lazy, this will be increasingly
Pushed
common.
to be lazy.
Well, because
not
like
is pushing anything.
I'm pretty sure, but like if the carrot is juicy enough, like people will want to like make their programs sort of start faster, right? Like that's
juicy
the
carrots. We like juicy carrots.
Yes, exactly. So, all in all, Sam fixed it such that when you are adding a module reference during imports, there is no longer a race condition that was causing sometimes like sys modules to be inconsistent. So yeah, like now when you're dynamically loading modules once threads were started, all of this is going to work. Because as you know this, there's going to be separate stacks. We already talked about this today.
Using
per
the episode.
thread, yes. But let's call it the database, the state of modules
database.
in your application, right?
Yes,
Whatever you like,
global.
the state of like what modules are there, that is still shared. The entire point of free threading is that you have this big shared state of data, and we treat modules and essentially any code that we have as data. We can mutate them from any thread at the same time. So yeah, Sam did that. I like that. It was a fun failure mode when it happened. It's a good bug fix. I love it.
All right, so Shamil fixed a data race in the struct module, basically to make it compatible with sub-interpreters. Funny enough, this race was found by Thread Sanitizer, so like that tool, when configured properly, can be quite nice. And this is quite important because like most of these things affect both free-threaded and sub-interpreters, and both mingle in a weird way. So like would work.
Yeah, like in fact, like we are still looking into edge cases on thread safety of the Sun library and improving that. And I think this is going to still take like a release or 2 or 10 to fully rectify. There is like a big kind of umbrella issue about making all built-in modules for thread safety. And as part of that, Yoni, the GitHub user Yoni, added critical sections to protect the states of readers and writers in the CSV module for the free threading build. So interestingly, this is already one of those things where we are getting increasingly high level and like kind of leaf modules. Like we're already sort of addressing particular those are still C-level modules, but particular use cases for making sure that like standard library modules can be used successfully in free-threaded builds. In this particular case, like unlikely edge case you would actually like find, but now we have like a proven correct implementation that uses critical section during reading and writing. In fact, like what I liked about this particular PR was that it did one of those things that a lot of people sort of skimp on, which is to add a reproducer case to the tests and actually prove that the new critical section does fix the race condition. So awesome. Thank you for this, Yoni.
All right, so after that, we have Edward Xu. So Edward fixed a performance issue in the data class init method. Basically, that was under free threaded, and they fixed this in basically using the deferred reference counting, which is a technique that we have mentioned a bunch of times previously in the podcast. And this is all also part of a big issue that was identified called basically poor thread scaling with constructing instances or accessing attributes. And this is like not only on data classes, it's on a bunch of other things, but the particular reproducer was using data classes. And here Sam and other people are like, looking at this closely. So we have a bunch of like, benchmarks and whatnot. And this issue particularly fixes the data classes per issue, which, like now ensuring that this thing scales properly. So a lot of future work in this particular issue, and this is just a small change, but important thing for you to have like real performance when you are actually using free thread in the future.
All right. Kumar Aditya improved thread safety and also made an optimization by skipping locking if an object is already locked by a toMutex critical section. So now, we are no longer releasing 2 locks when we should be only releasing 1.
It's an optimization on the critical section. Basically, if you're using the toMutex version of it, it basically avoids locking.
Yeah, because locking is skipped when we already know that like a particular object is already covered. So this was like a pretty tricky sequence of events to figure out. So like kudos for that. Like Kumar created like a gist where he actually explained this particular failure mode and created a PR reviewed by Sam Gross, landed awesome.
Amazing. So probably we will talk about this drama soonish in the next episode of our Stack series. But as part of the solution for some future drama that we will talk about, Victor Steiner added unstable thread state set stack protection and unstable thread state reset stack protections. So these functions that are in the unstable API are basically to manage the stack protections that Mark Shannon added recently to basically ensure that, if you call C functions from Python, you don't stack overflow. That will crash the interpreter. The problem is that, as you will see, this has like some interesting like consequences. And the idea here is that this will allow basically like some libraries like gevent and whatever is the other library that gevent uses, Greenlet, to basically like keep doing their stack switching mechanism without interfering with this. We will see, because like this particular issue is not finished, but this is such that people can use these functions and deactivate the stack protection in the threads that they create.
Right. Okay, this is only tangentially related to free threading itself, but it is very important in the world of free threading existing. You should not be mixing threading and forks. And the reason why is that this causes you to end up with dangling locks that can be, actually held by something that is not in the right process. So those locks will never be freed. And other resources can be in similarly inconsistent states. So do not multi-thread and fork. To this effect, we already had a warning that warned you if you tried to do this in Python. But this multi-threading plus fork warning was not effective when threads were stopped before the fork. Now, Steering Council member Gregory Smith actually split the OS API specific functionality to get the number of threads and so on, such that this case is covered. So the warning should be more comprehensive, and it will be more helpful now that I expect a lot of more people will be starting threads and not realizing that certain APIs in Python in your third-party libraries might be forking even if you don't know about it. So now we have this thing. You also can use it for whatever you want. That in OS you have register at fork, and you can actually just do things when Python notices that there is a fork happening. So this is where this particular warning is being put.
All right. So Michael Cho fixed basically the thread detection for TCL9 in the tkinter module. And the idea here is that the tkinter module APIs use different versions of things depending if they are running a thread or not. And depending on if it's the case or not, you need to call it in a different way. And that was part of the upgrade to the TCL9 and later stuff, because if you don't do this, you can get memory corruption or seg faults. And this is just like a thread identification, so we can properly call the correct things. So not technically free-threaded per se, but I'm pretty sure it will happen more on free-threaded.
All right, let's move to performance. And let's start with a big one, which is that the JIT that we are shipping is now changing from being trace projection to trace recording.
Well, that was a big one.
Yeah, that is a big change. I saw that first of all, the PR is huge. There was 200 commits. There's like 40 files that were actually changed during that. There were 6 people involved in reviewing it. Like also just the size of the change is big. But what does it even mean that like we're not doing trace projection, but we're doing trace recording now?
The idea basically is one of the mega changes that the JIT team is doing to ensure for 3.15 and 3.16 to ensure that the JIT is actually fast and not 0% fast.
Yeah.
And the idea here is that instead of look at the individual functions and whatnot and like JIT the all the different opcode stitching that you do, you basically record it. So when the function is actually executing, you record what the function is doing. So you don't need to guess. That's the basically idea. Like you don't try to predict based on like different signals and control flow and whatnot. Like you basically record these traces. This is more similar how the JIT works.
Yes, exactly.
Yes. And the idea is that you will start recording what the JIT is doing, and then you will use those things to basically decide what to JIT or not. This has some consequences. For instance, I was talking with Savannah, and she was saying that because these traces, basically you need to record them. So also that there is some
warm-up time.
Yes. Not only that, like apparently if these traces are too big, architecture when they cannot fit in the cache like suffer a lot. So for instance, her ARM Raspberry Pi was suffering a lot with this change because the traces don't fit in the L1 caches. But I mean, it may be fixed and whatever, but like it has some interesting consequences.
Yeah, but maybe you actually started with the cons there, but the pros of the change that like Kenjin already did, and the reason why he got interested in this like during the sprint is that this allows us to like already record and execute significantly more instructions than the previous JIT frontend, right? So even the original PR that he did this and that was mid-October, so like last month, like there was already 50% more micro ops executed, 30% more traces entered the last time we ran them. So, kind of it's like, it's a big improvement in actually the JIT being useful, being effective. So that makes me optimistic about this change.
I think the problem is that it doesn't work on Windows.
So far, it does not. In fact, yes, there is an open PR about that, which with VS 2026 will allow this, because what the PR depends on is tail calling. Like we need the tail calling interpreter or compute go-tos. And as we previously, laughed a lot, Visual Studio did not allow us to do this in previous versions. But with Visual Studio 2026, we are able to do this. So, this is coming soon enough.
Right. Yeah. Well, excellent work. Kenny is also working on more things, and I think one of the benchmarks that go actually quite faster with this is Richards, which is also a complicated one. So very cool.
Yeah.
So our one and only Mark Shannon implemented support for switch case dispatch with the tracing interpreter. Basically, this allows the JIT to optimize more even control flow. And this actually, unsurprisingly, increases the performance of stuff using the the pattern matching, for instance, when there's a lot of switch case things. And this is also a part of the big kind of overhaul of the JIT that is basically in this issue called trace recording JIT. So it just uses more the tracing interpreter to improve these traces in general.
Right. I have another change that is sort of related to like the switch to a trace recording JIT, and again by Kenjin, but something he just found last week, which is something that was responsible for a pretty big performance regression compared to the old JIT. Got missed in the flurry of comments and reviews at the end of that gigantic PR. So now he found that essentially instead of using deopt, we should use exit trace to enter executor. Like it's a detail like there, and it's a way smaller change than the big PR, but it improved the performance like quite significantly. So yeah, like good to see that like all of this is still in progress. We have a lot of time before 3:15, but we're getting there. This trace recording JIT is something that also PyPy people are more optimistic about. I think you heard Antonio talk last about how he expects that Python can get much faster, but not consistently so, and that's
Yes,
also
like,
something I agree with
fast,
that.
randomly fast.
Yes, but at least we need to have those happy cases. We need to allow those like ideal situations to be possible, and like Kenjin is working hard on making that happen.
By the way, one small clarification if you want to stitch it to the previous one. The PR that Mark Shannon did for the switch case dispatch. So this is also basically ensuring that the like interpreters, like in Windows, when you don't use compute to go to just use switch case, like the JIT still works.
Yes.
So this is linked to the previous one that we mentioned. All right. And then, so Savannah made a mega PR, basically extremely good work updating the JIT builds to use LLVM 21. So apart from, like keeping track with what LLVM is doing and leveraging the new stuff from LLVM, this is very important because LLVM 21 had a change, as we talk in the sprints by Bram Booker, that may allow the JIT to finally be debugged, to be seen. We have made some experiments with LLVM 21 on this, so it looks interesting. Like, still there is some mysterious unclear things, but like Brand mentions that of course we need to activate whatever he did to ensure that the JIT doesn't use the frame pointer register, and we can just basically skip the JIT when unwinding. But yes, this is very important. Actually, it was not easy. I was at PyCon Spain when she was doing this, and like she was running into all these problems because like LLVM changed the way they would do jumps, and like some of the relative jumps that they were doing now they are bigger, and like she had to like deal with like bigger jumps, which means that now she had to implement trampolines for the JIT because like you cannot just do arbitrary big jumps. So very, very good work.
Cool. Yeah. Not all performance optimizations relate to the JIT, if you can believe it, which is great because the JIT is so far experimental, and what is not experimental is byte array objects and bytes objects. So, until now, if you used byte arrays and you wanted a immutable version of that, so just bytes, that operation would actually be copying memory, which as fast as it can be done, it's still wasteful because it was copying. So now Cody Maloney added a new API that is called take bytes that allows you to just extract whatever bytes were already there in memory for a byte array and just reuse them inside a bytes object. So it is way more efficient because it is essentially zero copy. To do this, he needed to change byte array to actually have its internal buffer always be a bytes object. So smart. And thanks to this, we can actually expose this object to Python, use take bytes, and now make your Python level code more efficient. That is,
this kind of like a feature as well, right? Like it's kind of like optimization through a feature.
Yeah, exactly. Because like you just need this new method on byte arrays. But I love this because it's essentially like one of those things where you were thinking about, well, Python is so flexible, but like all of this copying is so wasteful. Oh, now we have an opportunity not to copy. That's
right.
good.
And I
good.
think he's also changing a bunch of the internal uses using this new thing. So
yes,
cool.
yes, exactly. So even if you don't use this directly, you will use it through Python, actually, depending on those things. So you should be seeing things getting faster. That's good.
Right. So Mikhail Efimov specialized the call list append instruction to not only apply to lists excluding list subclasses. And I should like this not only to ensure that we can treat it with the exact memory layout of lists and not like having to care about all the other things. But like this was also to basically fix a bug when by list we were specializing call list append on things that like were subclassing a list and was not particularly memory compatible, and it was basically crashing. So this is both like a bug fix and it can be an optimization because now you don't need to deal with like the other memory layout. So probably it's more like a bug fix than an optimization.
We can be really kind of hair splitting about where a particular change belongs. Like, for example,
well, there is a you don't need to so before the previous code for the PyList append thing needed to de-opt when it was not a cycle list, right? So now you don't need to do that because you're assuming that it only specializes for list, right? So
yeah, I agree with you. All I was saying is that the change that I'm going to talk about right now also sort of belongs in multiple categories, because when you care about free threading builds and you start adding critical sections where it's like, like this thing can be concurrently, change in parallel. So we need to make sure that people don't override the same internal data in ways that are incompatible or in ways that are invalid. Sometimes you will overdo it because it turns out that the internal operations were already guaranteed atomic by one or other way. So Yoni found 2 examples of this for frozen sets, and they removed the unnecessary critical sections for that. And it addressed a performance regression that we observed in set benchmarks. So, set and frozen set operations, especially during thrift, struct initialization and deserialization, is now faster after this optimization, or free threading bug fix. Hard to say, was made. So this particular change also belongs in multiple sections, I guess. Itamar Oren added a new CAPA functions to create a module object from a specification and an initialization function. So this enhancement allows custom importers to have more control over module creation. So that improves flexibility of the import system. And as far as I can tell, Meta in particular is interested in using that. So the motivation there was that it is not always possible, like in all scenarios, to create a module by directly calling the init function.
Yeah, basically this is the import leave loader create module function.
Exactly.
Like you can implement that if you are embedding CPython.
Yeah, so now this is going to be possible. Like it was also like a pretty fun PR to like read through. So yeah, like we are now more flexible in Python 3.15 in embedding use cases.
All right, now it's time for bug fixes.
Ooh.
So in the saga of the drama of the stack protection thing, Mark Shannon modified the Stack Overflow detection, which is a per platform system, to only raise exceptions when the stack pointer is about to overflow the stack. The idea here is that this small refinement ideally will help a lot with all the libraries like we mentioned, Gevent and Greenlet, but also like apparently Boost, C++ Boost, like coroutine implementation has like some version of this. So ideally this makes the whole thing compatible with this. To be seen, because like it's still unclear like what is the level of support for this and like the best effort, but we'll see.
So wait, let's take a step back. So this Stack Overflow detection, what is going on? So
this is for the next episode, Gukesh.
Yes, but also it is somewhat related to what we talked about already this time around. So in the classical Python 3.9, what we had was the stack was essentially by number of calls to Python functions, right? So we could literally say that your recursion limit was something, and when the stack was deeper than 1,000 entries, done, we're like raising a user exception, and that was always 1,000. It was very easy to think about.
Yes.
Now, with this new world, it is not easy to tell us 1,000 and it's always true, but also we want this number to be normally higher, but we cannot really specify what that number tangibly is going to be because the sizes of each stack entry are variable now. So yeah,
It's also because like the problem is that even if you are within that 1000 level, if you now call a C function that just starts like doing a lot of stack calls or whatever it is, like Fibonacci in C or whatever that is not is consuming the stack, you can still stack overflow.
Yes.
And of course, like that you cannot detect that because that's the illegal language way of managing things. But the other problem is that Python doesn't see like the proper like stack protection when you're interleaving Python and C functions. So you use, for instance, operator call from the operator module that consumes stacks. And like some of those we can see, some of those we couldn't see, and it's still possible that even within the stack overflow limit that we have, you can still stack overflow depending on how much are you consuming. Because like operator call is a very small function, but like maybe you are using some other library and that is calling back into Python again and again and again, and that bloats up. So this thing ensures that when we call functions, either they're in C or Python from within the interpreter, important because when we are not in the interpreter we cannot do anything, then we protect the interpreter from literally crashing. But the problem is that is platform dependent. All right, related to this actually, turns out that like one of the things that happen in Python with this mechanism is that in the HPPA platforms, which are certainly not even tier 3, I think. Well, maybe they are tier 3. Well, certainly not.
HPPA? I've never heard of this name before that issue. Like, what is that?
Isn't that like an architecture or something like that?
I think like it is an architecture because what they are referring to is Linux on HPPA, but like
Hewlett-Packard Precision Architecture.
Hewlett-Packard Precision Architecture. So it's a RISC architecture.
HP Precision Architecture. What the fuck is this? Is it for printers?
It is called Precision Architecture RISC. Or Hewlett-Packard Precision Architecture, and it was developed by Hewlett-Packard from the 80s until the 2000s.
Wow.
So it looks like this is not developed anymore.
But someone wants to install 314 there?
It is a big Endian architecture that like can be 64-bit. It is like normally it is either 16-bit or 32-bit. But it can also
it's because in this fucking architecture the stack grows upwards. Wow, that's fucking insane. Of course, and that like Mark Shannon nonsense will need like a minus sign for this architecture, no?
Yeah.
Yeah. So now we have a micro called PyStack grows down. yes. So this shows you all the different like nonsense that you need to deal with. Like you do platform specific behavior now in a language that it tries to be as much like independent from the platform as possible. Of course, like Windows the big three needs to be accounted anyway. But like in this particular case, you need literally to reverse the direction. A small fix, and someone can use Python 3.14 in their mega, HP system or whatever. But, at least this bug will serve as a post for future people that want to introduce weird platform-specific things in CPython.
Yeah, so what we usually tell people is that we very rarely actively break platform support for things that we don't want to support, like because why would you? That is unreasonable. But for platforms that we definitely don't support with our own core developers who know and use particular platforms, and platforms that we don't have any CI for, it is up to the actual users of those to come tell us about issues, and also in this case fix them. And this happened in this case, so we're plenty happy to allow some tweaks such that those things can be used on sort of esoteric platforms right now. Like maybe some listeners will prove us wrong, but like I literally never heard of this platform before stumbling upon this issue.
Right.
But what I did hear about is the warnings module. The warnings module is something that allows you to tell people that things are deprecated or that they shouldn't do a thing and whatnot. And you can do it either in Python or in C. And in fact, even if you do it in Python, it'll call into the C implementation unless that is not present. So it's going to use a pure Python implementation. And you know what? Those two did not agree. There was some differences in how like deprecation warnings were issued when dunder loader differed from the module specs loader. And so Serhi noticed this and fixed it. And ironically enough, like that fix was in August 2024, but it took a long while until actually this was merged, because there were some nits left on the PR, and it took us a long time to just essentially say, okay, we're gonna address them and land the fix. So sometimes when you see changes taking a long time, feel free to ping us, feel free to ask like what's actually left to do there, because like very often it's like, oh, okay, this is not ready to press the green button. There's only a small thing that I need to do, and you never get to do the small thing. So a fix that we might have had since August 2024 was sitting there for over a year. But it's how open source works,
right?
Yeah, I'm happy to see it now. Like it was essentially like found like during work on the newest PEPs.
Yeah, because Sergey has been like basically taking a lot of like care about the warnings module, because like he found a bunch of weird stuff after like some of the warnings that needed to be implemented as part of the recent PEP systems.
Yes.
Particularly I think it was the finalizer. It's PEP, like the not returning finally. So right now that was emitting a warning, and apparently Sergi discovered that the warning was like being duplicated, and like it was very inconsistent everywhere. And like, if you keep pulling from the thread, like you find all the weird shit.
Yeah.
All right. So now we have a bug fix from a Japan Perumal, which is one of those weird people that will, rare people, let's call it that way, that care about the AX platform that I'm so happy I don't need to deal with anymore. Is a hellscape. So apparently in the POSIX module, to check certain things about file descriptors, we're basically checking the proc pseudo file system. To obtain, for instance, like even the file descriptor number, you can check exactly what file is being referred by that and whatnot. And in AX, apparently, that is you need to still have the PID. Reason being that to know the file descriptors that you have open, you can do this nice trick in Linux at least, and many POSIX system, when you can go to /proc/self. And then you check the file descriptor, and that will list all of the file descriptor pseudo inode, and that will tell you all the file descriptor that you have open. Unfortunately, that alias to yourself doesn't exist in AX, because of course, so you need to use your own PID as anyone else's to just access it. So it's a small fix, and it makes the subprocess module work properly on AX.
All right.
So all the IBM people will, start dispensing bonuses.
Yes. I have another one that could potentially fit in multiple places because it talks about the JIT, but it talks about a crasher. So a bug that causes the Python interpreter to crash. So we got a report 3 weeks back that there was some pretty reproducible case that caused Python core dump, an abort with PyOptimizer optimize failing an assertion. So Mikhail Efimov found what the reason for that was and fixed it, which it turned out was setting the JIT attribute on the interpreter struct to false at finalization. Sounds like something you would want to do, but it turns out that in a rare case, it may be a problem when some optimized code is used after finalized modules. So now we actually don't do that at finalization, and the new tests that he added, with sub-processing, actually prove that this was necessary. So the JIT still very much experimental, but now a little less crashy. This fix was also backported to
0% crashing.
Yeah, yes, to 3.14.
And finally, Berg implemented a small, this is kind of like not a bug fix technically, it's kind of a feature kind of thing. I don't know. It's weird as well. So basically, if you have a process pool executor, right, using the concurrence features module, and then you have one of those, that spawns a bunch of workers, and then you give it them work. So if one of those workers crashes for whatever reason, because like maybe someone killed a process or the out of memory killer killed the thing or whatever it is, well, what happens is that you get this like error that basically says a process in the pool was terminated abruptly while the feature was running or pending. The problem is that tells you nothing about like what is happening. In particular, you don't know
which one.
Yeah, like if it was an exception, what was going on, and also you don't know the return value. The return value is quite important because at least in Linux, if your process was killed by a signal, you will get negative something, and that will tell you what signal it was and things like that. So. The fix is basically to implement like exception chaining. So apart from getting the broken pool process, broken process pool exception telling you that like this happened and the warning, you will also get like an exception telling you like what was the problem, like the PID of the process that terminated and also the exit code. So at least you can know that that was a sec for something.
But remember, because this is across processes, then like, it's not true exception chaining. It is literally string chaining, but at least you have all this information.
The exception that is basically reason and capture like now contains another one that has the metadata. And that's it,
cool. We thought we have enough material to talk about calling synchronously and then asynchronously next time. That those should be pretty nice, smooth episodes that will not go over crazy amounts of time. And what happened? What happened? Like as usual,
we fuck up. And now we are 2 hours and 11 minutes.
Man.
And we only talk about 1/3 of the frame call thing.
Okay, cool. Yes, I guess
we are bad at this.
You got sort of used to this, right? By now, when you're listening to this podcast, that we're rambling for a long time.
We should update the description and just own it. Like episodes have a random directions.
Expect more in part 2. See you next time.
See you next time.